Hello, today we are going to see another type of transducers which are called the inductive transducers. Inductance is another passive property, something similar to resistance. And from the basic principle, the inductance of a coil in henries calculated by the relation L equal N square A mu over L. And inductance is nothing but is a coil wound over a core. So it can be cored or can be air cored. Now the L is the inductance which is in Henry. N is the number of turns, number of coils around the core. A is the area of cross section. And mu is the permeability of the core, and this mu consisting of two parts, which is mu 0 and mu r. Mu 0 is called the absolute permeability, 4 pi into 10 raised to minus 7 Henry per meter, which is a constant term. Mu r is the relative permeability, which is nothing but a permeability with permeability of a medium with a reference to air. Therefore, if you are looking at the mu r of air or free space, it is equal to 1. And L, the small l, stands for length of the coil. So the inductance can be calculated using this particular relation. So normally in the case of inductors, the factors which is directly depends on L is the important factor is which is nothing but the number of turns. As long as the core is fixed, and mu is again the permeability which is dependent upon the medium, and the other factor is the length of the core. So these are the two parameters which is going to determine the value of inductance. Now there is another relation which is something called reluctance, and the reluctance is something but the resistance offered by the medium against the magnetic flux lines, which is something very similar to resistance but in terms of the magnetic flux lines. And the reluctance is calculated by the equation L divided by A mu, and this L divided by A mu already is appear in this particular equation. So if you substitute that equation, we end up with a new relation L equal N square divided by R. So where N is a number of turns and R is the reluctance of the coil. And again further, we are, if you're looking at some of the geometric form factor relation, which is connection between the area and the area of cross section and length. So G is equal to A divided by L. If you substitute, we will get the another suitable, convenient relation, which is L equal N square mu into G, where N is the number of turns, as we said already. Mu is the permeability of the material, the magnetic material that we use, and G is nothing but the geometric form factor. So these are the basic relation here. Now in the case of inductive transducer, one parameters or more than one parameters or one or more parameters, if you can change, then that will reflect on the value of L. And if you can do that, definitely we'll be able to transfer a physical form of energy into electrical signal. Okay. One of the important type of transducer belongs to the category of inductive transducers is the reluctance transducers. So already we said the reluctance is the property of the material. So by which the material try to resist the flow of or the passage of flux, magnetic flux lines. So in this particular model of reluctance transducers, this indicate the core of the inductor. These are the coils. So there is a coil is wound over the core, and there is a part which is the moving part or the displacing part. So when this particular segment is going to, vibrates or moving away, then this air gap will increase, and if it is moving towards the core, then the air gap will reduce. So because of this difference in the air gap, there is a change that is going to happen the magnetic inductance or the inductance of the coil. So this coil inductance will be directly depends on the air gap and how fast this air gap is going to change. So this is one type of transducers which is very common. It can be applicable to many products or many applications where some vibration is going to occur. Now, a similar application of reluctance transducers that can be used for the measurement of the speed. So, in this particular example, you will see that there is a wheel, a slotted wheel attached to what we call a coil around here, which is the inductive coil. And of course, there is a small gap is maintained between the coil and the rotating disc. It's a magnetic material disc. So what is going to happen is that if this particular slot is away from the magnetic coil, then definitely the gap will be maintained as minimum. So there is a minimum air gap is maintained. But once it is exactly coincides, or once it is in the proximity of the coil, then the flux density, the air gap will change. That will cause a different value of inductance. So whenever this particular coil, the slot which is approaches the magnetic coil, then there is a change in the inductance, and this change in the inductance can be used to measure the rotation of like wheels or in cars and so on. So many applications where it is required to measure the speed based on this type of transducers, which is the reluctance transducer. Another type of transducers, which is again from inductance family, which is the linear variable differential transformer transducers. This is also called Lvdt in short. So this another type where there are two sets of coils. This set of coil is the primary set of coil, the primary coil, and this side is we have got the secondary set of coil. So a single primary and two identical secondaries. Now the primary normally consisting of a large number of turns, and normally it is biased by a AC signal of normally at a power frequency or maybe higher frequency. And we have got a core here, and this core is a movable core. This core, it can be moved up or down, or up or down, this particular core. Then there are two set of secondary coils are there, and these coils are exactly identical, and they have connected in such a way that the output in these two coils are subtracted, or you will get a differential voltage at the output. Now the principle of this particular device is based on purely based on this particular core, and as we said already, this core is movable. And suppose there are some cases where we are supposed to measure, or it is required to measure the displacement or the vibration of a device or an equipment, then that vibrating part is supposed to connect it with this particular core. So if the part starts vibrating, definitely this core is also going to vibrate. So depending upon the position of this core, you will have an voltage. Now let us consider one case where the core is taking the upper part. It's moved to the upper part of the Lvdt. As a result, it is clear from the diagram that this core is covered the first coil or the upper part of the coil. As a result, this voltage will be more than this voltage. As a result, if the voltage across this particular coil is E1 and the voltage across this coil is E2, and let us assume that we have a voltage of E1 minus E2, and since E1 is more in the case of, in this particular condition, so E1 is more than the E2, the net voltage is going to be a positive voltage. On the other hand, if this particular core is exactly in the middle of the coil, then since in the middle of the coil, so that it is covered exactly, the covers the second, the upper part of the coil, secondary coil, and the lower part of the secondary coil. As a result, E1 and E2 will be almost zero. Practically speaking, it is very hard to get it balanced, but otherwise, ideally speaking, they're going to be zero. As a result, this particular voltage will be 0 volt. Similarly, if it is going below, the core is going below the coil, below the below the transducer, then what is going, or it is occupying the lower part. As a result, this voltage, E2, is more than E1. As a result, we are going to have a negative voltage in the other side. So this is the basic mechanism, okay, how the linear voltage differential transformer works. Ideal characteristics of a Lvdt transformer can be drawn as in the diagram. This part, we are just assuming that this is the positive voltage and this part is the negative voltage. This indicates the positive distance and this is the negative distance. So of course, it's an ideal graph. So that's the reason we are getting, when the object is, the core is exactly in the middle, we'll get a 0 voltage. As it moves away from the center towards the upper part, then definitely the voltage will be having a positive voltage and this side will be having a negative voltage. It has got better linearity up to certain extent, and practically speaking, there must be some amount of offset because of the mismatch in the coil, as well as the temperature difference. You may find some kind of offset. So practically speaking, you won't get exactly the graph like this. There must be some amount of offset here, positive offset, maybe negative offset, and that has to be corrected by means of the appropriate circuitries. Now we'll look at the advantages of Lvdt transducers. The first, one of the important point is the range of displacement that can be achieved by using this particular transducer. The high range is possible, like 1.25 mm of displacement up to 250 mm of displacement. It is quite big number, higher value compared to other type of transducers like reluctance type. Now the electrical isolation, since we are using Lvdt has got two coils with no common connectivity between the primary and secondary. So the primaries and secondaries are completely isolated. So this will give rise to safety in the case of operators. Now the third point is the better linearity compared to other type of sensors. Lvdt sensors has got a wide range of linearity. High sensitivity, it is also one of the point, is that whenever there is a small displacement, there must be a corresponding change in the output voltage. Then the ruggedness, it's a rugged structure, or the construction is, it is a rugged structure, so it will stay for long, durability and so on. If you look at the offset, disadvantages, one of the most important point is the offset issues. Okay, it is has to be corrected. So definitely, as we have mentioned earlier, we need to employ some additional circuitry for correcting this offset, and offset may not be fixed, so we need to have some adaptive system that can correct the offset issues. And similarly, the friction related issue, because it is based on the movement, so it is a friction related issues may be there. So of course, we have to do some kind of lubrication or some friction free movement or something has to be provided, or we need to have some special care on this particular issue. And the last point is, which is talking about the undue vibrations, because due to momentum of the system or inertia of the system, there must be a chance that there may be some kind of undue vibration, or again to give rise to the necessity for some kind of damping system or something. So this is the end of this particular part of sensor, which is the Lvdt sensor. So we'll continue in the next lecture about capacitive type of transducers. Thank you for listening.